In this video, we're going to go over Euler's method, which is used to approximate values of solutions to initial value problems. So when you have a differential equation, if you know how to solve the system, or how to solve the differential equation, then you know the function. You know the functions that satisfy the differential equation. But there are differential equations where you can't get a nice formula for the solutions. In fact, most of the time, you will not be able to find a nice formula for the solutions. So in that case, you can still approximate what the function looks like. So you can estimate the values of the solutions at certain values. And that's what Euler's method is about. So Euler's method is an example of something called a numerical method. So a numerical method is something that is used to approximate something that you want to find. And that is often used in engineering, like numerical methods for finding solutions to equations or finding things like eigenvalues in linear algebra. So if you hear numerical methods, that's what that's about. So Euler's method is an example of a numerical method, and it's the most basic numerical method for approximating solutions to differential equations. So Euler's method is used to approximate the values of solutions to initial value problems. And to explain what Euler's method is, remember that when you have an initial value problem, you have some differential equation. It's going to be like y prime equals some function of x and y, say f of xy, and you're also given some initial value, x0, y0. So y0 is equal to y of x0. And basically, the idea is, in Euler's method, you want to estimate y of a for some value of a. Okay. So here's a picture. Let's say that you have your differential equation, y prime equals f of xy. Well, at each x comma y, you're going to have a solution. As long as your differential equation is nice, there's a unique solution. So there's exactly one solution curve passing through each point. So let's say that your solutions to the differential equation look like this. Okay, at every single point, there's a solution curve. The solution curves don't touch. So the solutions fill up the plane. And let's say that you're given some initial condition. So let's say that x0, you're given some value y0. Then what's going on is that there's going to be a unique solution. And in this picture, the unique solution is the curve that crosses through the point x0, y0. So in that case, this would be this curve. So that would be the solution to the initial value problem. And like I was saying, sometimes you can find a formula for this curve, but sometimes you cannot find a formula for the curve. But you can still use the differential equation to learn something about it. So here's the idea. So again, we have some value a, maybe here, let's say, and we know that at x0, the y value is y0. Now at a, in this picture, y of a would be up here, right? So the question is, what is that y value? Well, if you don't know the equation of this curve, then you wouldn't be able to know exactly what that is. If you knew the equation of the curve, then it's easy. You could just plug in x equals a and then figure out what y is equal to. But if you don't know what the function is, right, what the solution actually is, then you will not know exactly what you get when you plug in x equals a, because you don't know what your function even is. But the idea of Euler's method is to estimate the value. So Euler's method isn't going to tell you exactly what y of a is, it just estimates y of a. And the idea is to use the tangent line approximation. So estimate y of a using the tangent line approximation, which I'm not going to go over because I'm assuming that you know what it is. There are lots of videos that go over how to find the tangent line approximation. Using the tangent line approximation repeatedly. So you use it many times. Okay, so I'm just going to say what the steps are to Euler's method, and then I'm going to do some examples to explain how it works. So the first step is you have to specify something called a step size. Which is typically called h. So the step size, what that means is it's the change in x. So Euler's method consists of several steps, and each step you take a step size, which is a change in x. Okay? Then once you specify what the step size is, you use the tangent line approximation with the change in x, delta x, equal to h, to estimate y of x0 plus h. Well, what is that? So y of x0 plus h, that's the y value when x is x0 plus h. And the tangent line approximation says that this value is approximately equal to y sub 0 plus y prime of x0 times h. Okay. Because basically your initial y value is y0. So that's your starting y0. And basically, when you increase x0, your starting value is x0, right? Then your new x value is x0 plus h. And the question is, what is the new y value? Well, it's approximately equal to what you get when you take your initial y value, which is y0, and then add y prime of x0 times h. Now, what is that? That is the change in x, so h is the change in x, and then this y prime of x0 is the slope of the tangent line. So if you take the change in x and you multiply by the slope of the tangent line, that gives you the change in y of the tangent line. So then when you add that to y0, you get the new y value. This thing on the right-hand side would be the new y value you would get if you plugged in x0 plus h into the tangent line. So if you just went along the line, the tangent line, okay, this by each units to the right, this would be the new y value you get. Okay, now it's not the same as y of x0 plus h because you're just using the tangent line approximation. So for example, you have some curve like this, and then let's say this is your x0 is corresponding to this value of x, and then if you plugged in, okay, a value into your tangent line, you're going to get some y value here, whereas the y value is actually up there. So it's not the real value, but it's the approximation. Okay. So you get this approximate value, and this approximate value is what you call y1. And this x0 plus h is your x1. So you started off with x0, y0, and now you're at x1 comma y1. So now you are at x1, y1. This is probably not going to be on the original curve that you started on. So you started on a curve that passed through x0, y0. Now you're on a new solution curve that passes through x1, y1. In general, those will not be the same curve. So now you are probably on a different solution curve. Remember, the solution curves fill up the entire plane. So wherever you are, you're on some solution curve. So you're probably on a different solution curve. But you still use the same approach. So now you use the new x1, y1 as your new quote-unquote starting point. Because you started at x1, y1, now you're at you started at x0, y0, now you're at x1, y1, but you can do the same thing as you did before. So now we're at x1, y1, we're going to get x2, y2. So you take x1, you add h, that's going to be your new x2. Okay, and then what you get when you plug in x1 plus h is approximately your original y value, which is y1 now, plus y prime of x0, or y prime of x1. But if you think about, so it's y prime of x1 times h. But if you think about what y prime is, okay, your y prime, we know, is f of xy, right? Because you have this differential equation. So actually, when you go back here, you could have written this y0 plus y prime of x0 times h as y0 plus f of x0, y0 times h. Now your f of xy is not the curve that you're on, okay? This f of xy is just whatever y prime is equal to in the differential equation. Okay, so those are equal. And so this y1 plus y prime of x1 times h is equal to y1 plus f of x1, y1 times h. Because again, y prime is equal to f of xy. So, of course, this value now, we would call this y2. So now you're at the point x2, y2, and you can just repeat the process. Y of x2 plus h is equal to y2 plus f of x2, y2 times h. And, this is approximately, right? It's approximately. And then this is equal to y3, and then you just keep, and then that's your x3, and so now you have this x3, y3, and then you keep going as many times as you need to get the value that you're looking for. So basically, you're trying to plug in A, okay? And depending on your step size, you take a certain number of steps to reach A. And once you reach A, then the y value you get is your estimate. So in general, you would use, well, x1 was x0 plus h, x2 was x1 plus h. I mean, your next x value is just what you get when you add h. So you get x sub n plus 1 equals x sub n plus h. And also the y values, y sub n plus 1 is going to be your previous y value, y sub n, plus the change in y, and that's f of x sub n, y sub n, so that's your y prime, right, times h. So these are the equations that you use in Euler's method. So let's put this in the box. But it's important to know where these formulas come from. Okay, this first equation is just saying that you add h to get your next x value. The second equation is saying that you get your next y value from the tangent line approximation applied to the previous y value. So let's look at an example so that we understand what's going on. So let's say that you have this differential equation y prime equals x plus 2y. And you know that y of 1 is equal to negative 2. Use one step of Euler's method to estimate y of 3 over 2. So first of all, let's make sure we understand what's going on. So you have some differential equation, okay? There are a bunch of solutions to y prime equals x plus 2y. But when you specify that y of 1 is negative 2, that initial value is going to specify exactly one curve. So there's exactly one solution we're talking about. It's the function that satisfies y prime equals x plus 2y, and when you plug in 1, you get negative 2. There's only one function that does that. And the question is, approximate what you get when you plug in 3 over 2 into that function. So that's what the question's asking you, and it's asking you to do it using one step of Euler's method. Well, one step of Euler's method is just the tangent line approximation applied once. So we're really just using the tangent line approximation. So the first step is to find h, but before we even find h, let's just understand how this example gives you these previous functions. Like, what is the f of xy? What's the x0, y0? Okay, so in this case, the problem says y prime is x plus 2y. So this x plus 2y, that's your f of xy, okay? Your initial value is, when you plug in 1, you get negative 2. So x0 is 1 and y0 is negative 2. Okay, and we're trying to estimate y of 3 over 2. So the first step, before you even do anything, is to figure out what the step size is. So what is the step size? Well, let's think about it. So we're given our initial value is x0 is 1. Okay, that's our initial x value. And where we're trying to end up is when x is 3 over 2, because we're trying to estimate what you get when x is 3 over 2. So our starting x value is x0 is 1, and our ending value is 3 over 2. And we want to use one step of Euler's method. So we're just going to have an x1. Our x1 is 3 over 2. So what is h? Well, h is the difference. H is how many, h is what's the change in x in each step. Well, if you have to go from 1 to 3 over 2 in one step, how many units do you go? Well, 3 over 2 minus 1 is a half, so our h is a half. Okay, that's one step. So our step size is a half. H is 3 over 2 minus 1, which is a half. So now we're ready to use Euler's method. So for using Euler's method, I strongly encourage you to make a table, because if you don't make a table, it just makes everything very complicated because there's too many numbers in random places. So I recommend that you make a table where the first column is n, okay? your second column is xn, your third column is yn, and then your last column is f of xn, yn. So that's your y prime, f of xn, yn. It's a y prime evaluated at xn. So if you want to be super specific, it would be, instead of y prime, it would be y prime of xn. Okay. But I'm just going to write y prime. So our initial value is when n is 0, right? So when n is 0, our x0 is 1, and our y0 is negative 2. How did we get that? We're told that in the problem here. And what else can we easily fill in? Well, we can fill in that we're going to stop at n equals 1. And when n equals 1, what's x sub n? X sub 1 is 3 halves, right? So what we're looking for is y sub 1, because that's the approximation after one step, y sub 1. So we need to figure out what number goes in that slot. And once we find that, then we're done. So now we need y prime, so that's y prime of x0. So what is y prime of x0? Well, you look at your differential equation. Y prime was x plus 2y. So if you plug in x0, y0 into your f of xy, okay, into your x plus 2y, you get 1 plus 2 times negative 2, and that is 1 minus 4 is negative 3. Okay, so now we're ready to find y sub 1. Y sub 1 is y sub 0 plus h times f of x0, y0. So that is equal to, now you just look at the table. Y sub 0 is negative 2, h we know is a half, and then f of x0, y0 was negative 3. So now we have to figure out what this is. Negative 2 minus 3 halves equals negative 7 over 2. So the answer is negative 7 over 2. So that is what y of 3 over 2 is approximately equal to. Now, no one's saying that that's actually what you get when you plug in 3 over 2 into y. We're just giving an estimate. Okay. So that's Euler's method in one step. Let's do another example. Let's do the same problem, but using 2 steps. So before we did 1 step, right? Now we want to do it using 2 steps, but we have the same problem. We have the same differential equation. We're still trying to estimate y of 3 over 2, but we want to do it in 2 steps instead of 1 step. So basically our n is going to be 2. Well, what is different? What's different is going to be our h. So we started off with 1, that's our x0, okay? But now we're trying to end up at 3 over 2 again, but we want to do it in 2 steps. So that's going to be our x2. And we're going to have an x1 in the middle. So the question is, what is h? Well, h is going to be halfway between how far we want to go. H is the step size, right? That's this distance, and it's the same as that distance. Now, technically, you could use 2 steps of different sizes. So, but usually you want to use the same size because it makes things easier. So we'll just have h plus h equals the total change in x. Well, what's the total change in x? We know that to go from 1 to 3 halves, that's half a unit. So our h is going to be half of that. So our h is, I'll just write it out. It's 3 over 2 minus 1, so that's the change in x, and then divided by the number of steps, which is 2. So that's going to be 1/2 divided by 2, and that's 1/4. So our step size is 1/4. So that's our h, and now we're ready to set up the table again. So we have n, x sub n, y sub n, and then y prime, which is f of x n, y n. And this time we need 2 steps, so where n is going to go from 0 to 2. Our x's we can fill in. We know that x0 is 1. x1 is, well, it's 1 plus h. So 1 plus a half is 3 halves. And then you add h again and you get, oh, no, it's not. It's, you add 1/4, right? 1 plus 1/4 is 5/4. And then that plus 1/4 is 3/2. So just keep in mind that each time n goes up by 1, you're adding h. Right? So in the previous one, to go from 1 to 3/2, you added h, which was a half in the previous example. Oops. So, okay. So now we're ready to use Euler's method. So our y0 was, what was y0? -2, right? That's what it said in the problem. Yeah, y of 1 is -2. And now we're ready to just use Euler's method. So I'm just going to erase this plus h because I normally don't put that there. So y prime, okay, our y prime of at x0 is equal to f of x0, y0, right? So I'm just going to do it up there. So I get 1 plus 2 times -2, which is -3. So just to remind you where that came from, it was because in this problem, our y prime was x plus 2y. So I'm just plugging in x0 for x and y0 for y. That is going to give me 1 plus 2 times -2, which is -3. So now we can find y sub 1. Y sub 1 is y sub 0 plus h times f of x0, y0. So that's going to be -2 plus, our h was 1/4 this time, times -3. So that's -2 minus 3/4, which is -11/4. So that's our y sub 1 that goes in the table. Now we need to find y prime again, so we use the formula. In fact, I'm just going to write down, why don't I just write down, so y prime was x plus 2y. I'm just going to write down x sub n plus 2 times y sub n. That way I don't have to keep looking at it. So now we do 5/4 plus 2 times -11/4, and that's going to be -17/4. Now we're ready to find y2. y2 is y1 plus h times f of x1, y1. So that's going to be, our y1 was -11/4, our h is 1/4, f of x1, y1 is -17/4. Now we just need to know what that is. That turns out to be -44/16 minus 17/16. That's -61/16. So that's going to go in our table. That's the final answer. Oops. Because we did Euler's method using 2 steps. Okay. So one of the common mistakes that you see on exams, if you're grading exams, is that a lot of students will either get the wrong h, or they'll do too many steps in Euler's method, or not enough steps. So it might turn out that you have to do 3 steps in Euler's method, but then they did 2 steps. Or they were only supposed to do 2 steps, but they did 3 steps. And then they ended up doing more work than necessary and still got the wrong answer. So just make sure you know exactly how many steps you're taking. And usually the problem will, they might not tell you how many steps to take, but they'll tell you. So in this problem, oh yeah, in this problem they told you how many steps to take, but they didn't tell you the step size. And you figured out the step size by looking at the total change in x. Okay, so that's your final x value minus your initial value divided by the total number of steps to figure out what h is. In the next problem, we'll do an example where they give you h, but they don't tell you how many steps to take. So let's do one more problem. This is a different differential equation. So let's say that we have the differential equation xy prime equals 3 plus xy, and the initial value y of 1 is negative 1. And it says, use Euler's method with step size h equals 0.5 to approximate the solution y of x at the point x equals 2. So in this problem, they give you the differential equation, they give you the initial value, they give you the step size, and they ask you to use Euler's method to approximate the solution at the point x equals 2. So first of all, when it says the solution y of x at the point x equals 2, what that means is y of 2. Okay, so you're supposed to give an estimate for that number. So what is that number approximately? That's the question. So here we're given the step size, but we're not told how many steps to take. Well, how are we going to know how many steps to take? Well, look at what we're given. We're given our our x0 is 1, our y0 is negative 1, and we're trying to end up at x equals 2, right? So let's draw a little number line. So our x0 is 1. We're told that we have to use the step size h equals 0.5. So each step you're taking, you're going to the right by 0.5. And where do you want to end up in terms of the x value? You're trying to approximate the solution at the point x equals 2. So here's x equals 2. Now if your h is 0.5, you're going to the right 0.5 each step. So how many steps are you going to take? Well, you're starting at 1. You're trying to end at 2. So how many units do you have to go to the right? 1, because it's 2 minus 1 is 1. So you're trying to go 1 unit, okay, and each step is 0.5. So if each step is 0.5, how many steps will it take to go 1 unit? 2. So the number of steps is 2. Okay? So our h is 0.5. So after 1 step, you're at 3 over 2, because it's 1 plus a half is 3 over 2. And then if you add half again, you get 2. So that's h. One more time, 3 halves plus h is 2. So we have to go 2 steps. Okay, so let's write that down. So 2 minus 1, that's the total change in x, divided by the step size, that's a half, is 2, which is the number of steps. So now we're ready to set up, well actually, we're not quite ready to set up the Euler's method, because look at the differential equation we have. It's x times y prime equals 3 plus xy. Now to use Euler's method, you have this y prime equals f of x and yn. Right? This y prime equals f of xy. Where was it? Up here. And so you need your f of xy in order to use Euler's method. So in this previous example, we had y prime equals x plus 2y. That was our f of xy. If you look at this example, is y prime by itself? No, it's not. There's an x times it. So what do we have to do? We have to divide both sides by x, because we need y prime equals something to be our differential equation. So we are going to take this differential equation and divide both sides by x. So we get y prime is 3 plus xy over x, and I'm just going to simplify that to 3 over x plus y. So that's our f of xy. That's what we use. Okay, so now we are actually ready to set up our table. So here's n, x sub n, y sub n, and y prime, which is f of x n y n, which is 3 over xn plus yn. And our initial, so we're going to take 2 steps. So we have n going from 0 to 2. Our x0 we're given is 1. And then our step size is h, which is 0.5. So in one step, we're going to be at 1 plus a half is 3 over 2. And then when you take another step, 3 over 2 plus a half makes 2. And our y0 is negative 1. That's given in the problem. So now we're ready to just use the formulas in Euler's method to just fill out the rest of the table. So our y prime, that's f of x0, y0, that's 3 over x0, 3 over 1 plus negative 1. That's 3 minus 1 is 2. Now we need y1. So y1 is y0 plus h times f of x0, y0. So it's the same in all of the Euler's method problems. I mean, you use the same equations. So you get y0, which is negative 1, plus h, which is a half, times f of x0, y0, which was 2. So if you figure out what this is, you get 0. Now we find our f of x1, y1. That's 3 over x1, so that's 3 over 3 halves, plus y0, or y1, which is 0, and then the result is 2. Oh, we got 2 again. It's just a coincidence. Y sub 2 is equal to y sub 1 plus h times f of x1, y1. And then this is equal to y sub 1 was 0, and then you have h, which is a half, and then times f of x1, y1, which is 2. So the answer is 1. That's our answer. And again, we know that we stop here because the question was to approximate the solution at x equals 2. And after 2 steps, we're at x equals 2. So don't, keep going and fill in more and more of the table. Make sure you know when to stop. So that's a common mistake. So common mistakes, again, are the wrong step size, the wrong h, and then too many steps or too few steps in Euler's method.